The next speaker in this session is Andrew Wilson. Andrew is in his third-year PhD candidate at Brigham Young University, focusing on reliable soft processors implemented on SRAM-based FPGAs for space applications. He has worked 4 summers at NASA Goddard and 3 years at L3 Harris as an FPGA engineer. His YouTube channel, which by the way I recommend, focuses on providing educational videos on advanced FPGA features. He wants to provide public examples integrating vendor and open source tools to optimize FPGA usage across all fields. Andrew.
We good? Yeah, sounds good. Okay, let's get my slide up. So yeah, I'm Andrew Wilson. I'm here to present on post-radiation fault analysis of high reliability FPGA Linux system on chips. I would like to take a moment to thank my collaborators and my advisor, Mike Wirthlin. So at Brigham Young University, we've done a lot of radiation testing for FPGA space application over the past decade or two. And we have developed a lot of techniques for testing and applying fault-tolerant methods to our digital designs to take a COTS or even a rad-hard FPGA and in the design improve it so that it's more resilient against radiation effects. In our recent testing, we have been using more and more complex digital designs, and our reliability techniques aren't working as well as we hoped. So to better understand how our fault-tolerant designs fail, BYU has developed a bitstream fault analysis tool. And with this tool, we want to be able to understand how our fault-tolerant design is failing and be able to better understand how we can improve the reliability techniques so that we can produce a more reliable netlist and digital design for an FPGA. So first, with FPGAs in space, they are often used for critical applications. FPGAs allow for a flexible hardware system, often interconnecting with unique sensors and actuators. A good example is the Perseverance Mars lander, which used several rad-hard Vertex 5 processors to perform real-time calculations for the landing on the Mars surface. We also have Ingenuity, which tagged along with Perseverance, is a Mars helicopter, and it's using a microchip ProASIC FPGA as well as 2 Snapdragon processors for its control system. Radiation affects FPGAs in many different ways. You've probably heard of total ionizing dose or single event effects. In this situation, we're going to focus on single event upsets, which is a change of state caused by ionizing particle striking a gate. We often induce this effect on FPGAs via neutron testing at Lance facility in New Mexico. You can see our picture where we have several FPGAs lined up in a row where our neutron particles will go through all of them. And when a neutron particle goes through and upsets the configuration memory, it can change the functionality of several different parts. This includes the LUT configuration, the routing, and as well as memory, including the flip-flops and DRAMs. There are ways we can mitigate against these upsets. A popular method is triple-modular redundancy, or TMR. TMR triplicates your digital design and then inserts voters, and often triplicated voters, in the design. You can do a block level TMR, or you can do fine-grained TMR, trying to create as many TMR domains as possible. We also do additional configuration scrubbing to repair any upsets during operation, so that these upsets do not accumulate in our design. When both these techniques are implemented successfully, there are many works showing that you can get a 30x improvement in your mean time between failures. So for our design, we're targeting the Xilinx family of FPGAs. Xilinx offers a rad-tolerant package for their Kintex UltraScale device. And even Xilinx recommends the use of a TMR microblaze module when using this device. Our design that we wanted to test is a RISC-V system on chip. This includes a DRAM module and caches and runs a Linux kernel on the processor. We then use BYU's SpiderNet TMR tools to apply fine-grained TMR to the netlist. And this allows us to integrate closely with the Vivato tools and is quite easy to implement. But this TMR has a costly overhead for its protection. Our LUT utilization increases by 4x. Our LUT-RAM, flip-flops, and VRAMs and other DSPs and primitives increase about 3x. And our max frequency in this situation decreased about 20%. Though it's from design to design how much your max frequency will decrease. And you can see the floor plan of the unmitigated design on the left and the mitigated design on the right. So we take this design to Lance. We have 7 days of continued testing. So 24/7, the beam is going, and we're trying to collect as much data as possible. We are targeting the Arctic-7 FPGA. We do about 2 days with the unmitigated design and about 5 days with the TMR design. We have a JTAG device that is continually reading the configuration memory and scrubbing it. And we're able to record any upsets that we see during this testing phase. In our recent test, when we tried to implement this advanced or complex system on chip, we only saw about a 14x improvement in mean time between failure. But in the previous slide, we had a decrease in our max frequency by 20%. So we need to calculate that as well. So we had only a 12x improvement in our mean work between failure because our performance decreased. And before, at the beginning of this presentation, I talked about many other works saw a 30x improvement. So we want to be able to understand why we didn't get our 30x improvement. So we've been working on a fault analysis tool. And this tool allows us to take a CRAM upset that we observed and identified as a critical sensitive bit and be able to identify how that causes our design to fail. So the different inputs into our fault analysis tool is the address of the sensitive CRAM bit, the design checkpoint from Vivato, which includes the routing, the net names, and other important information, and also the design bitstream that we use for the FPGA. Currently, these tools are only targeting the Xilinx 7 series family. So our first goal is to identify the CRAM bit. So when we have our FPGA at the test next to the neutron beam source, we have on the bottom shelf there a JTAG scrubber, which is another FPGA. We have a Zinc FPGA doing high-speed continuous JTAG scrubbing. And we're able to log all the upsets that we see during the beam. And we take our upsets and we identify through correlation to our processor output what is likely causing our failure. We then take that to a fault injection back at BYU and verify that that bit caused the failure within our design. So we're able to identify our sensitive bit. Once we have a bit, we now need to identify which FPGA design resource it's a part of. So we use the open source Project X-Ray database, which is a tool that the open source community uses to generate bit streams for these devices. And what we're going to do is we're going to do it backwards. We're going to take the bit stream and go backwards and figure out what that bit is in our design resource. So for this specific bit, it is part of a interconnect tile and is related to these 2 pips in the interconnect. So now that we know which part of the FPGA is, we then can look at our design checkpoints and identify the netlist portion. So using RapidWrite or Vivato, we're able to take this pip that's a part of the interconnect and see that it is an input net for a input SerDes primitive on the IO bank. Our other pip, which has a long net name, is actually a triplicated address signal for the processor cache. And now we know which nets we're dealing with. We then can see how the failure in the interconnect would cause the system to fail. So in this situation, we have an interconnect and we have our original signal. And with the bit flip in the interconnect, we cause a short. So looking at the full interconnect block, we have the iSerDes net yellow. We have the cache address blue. And the red line is the pip that we activated. So now that the SerDes address is now writing to the net, that is the iSerDes. So the cache is writing to the iSerDes net in that situation. So this tool, we're now going to apply it to our system and try to identify as many single point failures as possible and figure out what is our main issue within our fault-tolerant system. So when we took the design to LAMPS and did the neutron test, we collected about 27 failures. But we wanted to collect additional failures so that we could have a better subset to look at. So we performed random fault injection, probably for maybe 2 days, and collected about 200 injections and additional upsets, or additional sensitive CRAM upsets to get 106 sensitive CRAM upsets in total. And this is using random fault injection. We didn't do the complete design, but using this number, we can see we have about a 0.05% sensitivity, which relates to about 2,500 sensitive bits in the full design using statistics. So then we can take these 106 bits and try to identify the design resources through Project X-ray. Most of the failures occurred in the interconnects, the routing of the design. We also had several failures, about 20% or 18%, in the I/O pins, or close to the I/O pins. We can't triplicate our I/O unless we had like triplicated DDR memory on the outside. So our TMR mitigation doesn't affect that. And we also have some undefined bits where we can see that the open source tools are cannot properly identify all the bits in the bit stream. Then we take these resources and we relate it to our design netlist. We can see that the DDR interface was a majority of the failures. We can also see that 20%, or about 19% were clock networking, or were part of the clock network. We were supposed to have a triplicated clock network, but using this tool, we identified that our network was not triplicated in all situations, that Vivado in the place and route stages did optimize our mitigation away. So this help us identify that issue and hopefully resolve it in our next iteration. And there are other failures with the constant logic, the VCC and ground in the device. The net list considers all VCC and ground points on the FPGA to be one net. So it's hard for our TMR tool to be even able to target that as well. And there's reset circuitry along the I/O banks that is, there's no way to mitigate that as well. So here are a few examples of the output of our tools. On the top left, we have the text output. And in this situation, I know it's small, but sorry, we identify the address. We identify that it's a 0 to 1 flip. It's an interconnect block. We have the pips. And then we look at the affected resources. And in this situation, we have a iSerDes block and the triplicated flip-flops that come after it. And we can see that the net in the floor plan, we have this long net going through our design. That net is not protected. Any upset in that net from the TMR block to the I/O will cause single point failures. And in this situation, there was one interconnect where we saw the earlier example where we activated a pip and corrupted one of the nets. The next is a similar example. In this situation is about the output from the TMR voter to the OSERDES output. We have two reduction voters going to two different OSERDES devices. And there is an interconnect block on the right next to the I/O blocks, where we have the red lines are the two different reduction lines. And then we have the blue line in the interconnect, which is causing a conflict and upsetting one of the nets going to one of the OSERDES, and which will corrupt our data that we write to DDR. We now have a LUT example. So this is a bit. It's part of the CLB and part of the LUT configuration. In this situation, we're corrupting the 11th bit of the initialization string. And this causes our reduction voter to not be a voter anymore. And so when our TMR, our 3 domains, are reduced to 1 domain to go to the I/O, it has a corrupt output. This last example kind of demonstrates how we realized our TMR clocks were not TMR for this specific example. We have a deactivation in the interconnect for clock routing mux. And what happens is that the clock was turned off locally for these different primitives in the FPGA design. We have 3 shift registers, And all three are on the different domains. So when the clock turned off, our TMR had an immediate failure with these shift registers. So now that we have the results of this bitstream fault analysis, we can figure out how we can improve our design. First, we can verify that our triplicated clock network actually exists after place and route. Usually, the best way to do this is just use the don't touch parameter. Next, we can use placement constraints for our TMR domains, our I/O rotors, and our flip-flops. You can see in the picture on the right, we have separated our TMR domains with the 3 colors. And on the very right, we have all our DDR primitives are located as close as possible to the I/O bank to prevent long, unprotected nets. We can also do protocol levels, protocol level protection for our DDR, like single error correction, double error detection, error correction codes. And with DDR4 and forward, we can also use address command parity. We can also look at any other I/O that could potentially be on the device and figure out how we can protect the data that's being transmitted across those. For resets and constraints, for resets and constants, like we talked earlier, we have yet to figure out a good method to protect against those. So theoretically, if we were to apply all these improvements, we would see a reduction of interconnect failures by 9x, a reduction of clock failures by 6x. And though the other elements we cannot, we don't have a strong strategy at the moment to be able to reduce those failures. But with those improvements, we can reduce our 106 sensitive bits to 23 sensitive bits. This would be a 4.6 improvement over our baseline TMR test, but also a 68x improvement over our non-TMR unprotected design. So in conclusion, when we started testing with our complex fault-tolerant TMR RISC-V system on chip, we lacked the TMR protection that we wanted to see. So we were able to perform bitstream analysis using open source and vendor tools to identify these single point failures. We then categorize them so we know what protection would be best applied to be able to reduce it as much as possible. And we hope that we plan to see an improvement in our TMR by 4.6x in our next experiment. And yeah, basically for our future work, we plan to apply these mitigations, use fault injection to verify that they actually work, and then hopefully go to neutron radiation testing so we have the data to show the improvement of our new TMR methodology. Thank you.
We're running a little bit late, so we have room for a few questions.
Hi. Thanks for an interesting talk. I may have missed it, but how many separate boards did you use in the testing?
How many separate boards? Yeah. That's a good question. In this experiment, I think we would had probably use 3 different boards. And we kind of rotated what we're doing, the non-TMR and the TMR. But in connection to that, we have seen board-specific failures, and it was mostly related to the DDR timing. The different boards had different DDR timing training values.
Yeah, I was just curious as to whether the bits you'd identified as being sensitive were due to that piece of silicon, or whether it was statistically relevant. That kind of something.
So you're saying if there's different silicon had different
different characteristics.
Yeah. Mostly, we haven't seen anything in like the routing or the LUTs. It's usually something that is done, usually something software-wise or flip-flop-wise that is unique for that FPGA, where if you turned off that flip-flop, it would cause an issue. We haven't seen anything unique in like the LUTs or the routing so far.
Okay, thank you.
The person behind you has another question.
Thanks. I guess I have a couple of questions. So one is, to go into space, how reliable do you need it to be? So you believe you could get a 68x improvement? Is that enough, or do you need rad hard, or do you need rad hard plus TMR? Like what do you need to kind of hit the absolute threshold?
That's a good question. There's a lot of different parameters. One is your orbits. LEO versus GEO are higher. You're going to see a lot of different radiation values. For instance, if we take the International Space Station, there's quite a few FPGA experiments on the International Space Station. And those, let's see, the Kintex ultrascale device, those usually only see one upset a week. Very, very small. But if you go to different orbits, you can see a lot more. But it's also the functionality that your FPGA is. Is your FPGA a critical function, or is it more data analysis? And also, how long does your FPGA need to do that function? Is your FPGA running constantly, or is there a very small window where it needs to be fault tolerant?
Thanks. I think another question I had was, so you're looking at bit flips in the configuration memory. I don't know if you looked for this or not. Do you see any flips in the user state, like the registers, transient delay errors due to just logic having a charge event? Are those things that you look for, and are they common enough to worry about, or does configuration memory dominate everything else?
So yeah, the quick answer is the configuration memory with SEUs does dominate everything else. So that's kind of the lowest hanging fruit to look at first. But to continue on, our TMR techniques do write the flip-flops correctly. So if the flip-flop is corrupted, it will be corrected. And in these experiments, we were using VRAMs, but we did not protect the VRAMs. We did not do any monitoring on the VRAM upsets as well. So there is a set of our failures during the radiation test that could be VRAM upsets that we don't know about.
Thanks.
Thank you very much. Thanks to speaker again.